for me. Well, um, so I am a imaging science alum, and yeah, and I'll just do my talk. And if you have any questions, feel free to interrupt me. I'm happy to take any questions, and there will also be some time for a Q&A at the end. So let's share. Okay, so I'm going to be talking about my mathematical art today. Um, Something that I really enjoy is painting, and here I am with one of my paintings about the fast Fourier transform, which is what I'll be talking about today. So a little bit about me. Let me just move this, whoops. So I did my undergrad in imaging science, and I did a minor in computer science, and I graduated in 2009. And after imaging science, I went to University of Washington in Seattle, and I did my PhD in computer science and engineering, where I studied computational photography and computer vision. And some exciting things that I did in grad school. I got to work with light field cameras, which are like these cool 3D cameras that you can refocus. I did some internships at Google and Microsoft Research, and I was an NVIDIA graduate research fellow, and I got really into writing CUDA code for a while. That was like my thing. But unfortunately, while I was in grad school, I actually experienced a lot of really serious medical issues. So I had to sort of go on medical leave on and off. And while I was on medical leave, I took up painting, and I decided to start making mathematical art actually during the pandemic. So here's a picture of me at CVPR where we're presenting a paper. This was a really fun project. And you probably have heard my name, like if you take any of Roger Easton's classes, I guess I'm still here on the syllabus. I'm this person, former undergraduate student Juliet Bernstein, which is my maiden name. And I have this video about signal show. I'm just going to share my audio. Oops. Let's see if I can play this video.
Signal Show is educational signal and image processing software. It can be used to demonstrate convolution in one dimension or two. Create linear combinations of special functions and modify them with operators. Operators are saved as variables and updated. Here we've created a complex chirp function, integrated the chirp function, and plotted its imaginary part versus its real part to create the beautiful Cornu spiral. Here, a system models the degradation of an image with a point spread function and noise. Blur the image more by making the point spread function wider. Modify 2D functions through their x and y components, or through their radial and angular components. There are many special built-in functions, such as this one, which can be used for sparse aperture imaging. Use the functions you've created in demonstrations. This demonstration builds up a square wave from its component frequencies. In this filtering demonstration, high frequencies are shown in red, middle frequencies are shown in green, and low frequencies are shown in blue. With Signal Show, the demonstration possibilities are endless because you create them yourself.
All right. And what I'm going to be talking about in this talk is my mathematical art. So, as I mentioned, during the pandemic, I got really into painting these mathematical pieces. So this one is about the prime factorization of the integers, and it's one of the first ones that I did. Um, I'll explain how I make these, but this is just a sense of what they look like. And this is the scale. This was 2021. And here's another similar one. And what I do in these paintings is I represent numbers with little symbols, and I visualize patterns in the prime numbers. Here's a picture of me with this painting, and another one. I'm going to play a video about this. Oops. Twin Primes for Hours by Juliet Fiss. This painting is a mathematical visualization of the prime factorization of the first 1200 integers. The numbers are arranged in a continuous snaking around pattern. The first row reads from left to right and contains the numbers 1 through 29. Here's 1, 2, 3, 4, 5, and so on. Here's 28 and 29. At 30, the numbers snake around and change direction. The second row reads from right to left and contains the numbers 31 through 59. Here's 31, 32, and so on. At 60, there is another switchback. The third row reads from left to right again and contains the numbers 61 through 89. The last cell, in the lower left corner, contains the number 1200. Prime numbers are represented by solid squares, each with a unique color and symbol. Composite numbers are represented by a combination of colors and symbols of their prime factors. The first prime number, 2, is represented by the color dark gray. Multiples of 2 contain a small dark gray dot. For example, the number 4 contains 2 small gray dots because 4 equals 2 times 2. The next prime number, 3, is dark brown. Multiples of 3 contain a small dark brown horizontal dash. For example, the number 6 contains both a dot and a horizontal dash because 6 equals 2 times 3. The next prime number, 5, is gray. The prime number 7 is red, 11 is orange, 13 is yellow, and so on. Many patterns and symmetries can be discovered in this visualization. Multiples of 2, 3, and 5 are found along vertical lines. These are the multiples of 2, the even numbers, the multiples of 3, and the multiples of 5. Prime numbers greater than 5 can be found in the remaining columns, which create a striking symmetry. The numbers are arranged continuously in this piece to more easily visualize prime gap. Prime gap is the difference between two successive prime numbers. For example, 29 and 31 have a prime gap of 2. Pairs of prime numbers that have a prime gap of 2 are called twin primes. 29 and 31 are found in the top right corner. 29 is a light blue squiggle, and 31 is a dark blue squiggle. Notice how they appear as prime factors. They travel together and form diagonal lines that crisscross the grid. Here's 59 and 61, another pair of twin primes. You can see the multiples of 59 and 61 travel together. Here's 2 times 59 and 2 times 61, 3 times 59 and 3 times 61, 4 times 59 and 4 times 61, 5 times 59 and 5 times 61, and so on. Some twin prime pairs, as well as other primes with a larger prime gap, are depicted with related symbols. What patterns can you find? All right. And just checking, is the audio coming through all right on the videos? Okay,
Yes.
great. Um, so this is another one. The algorithm to find all of the prime factors of the numbers is called the sieve of Eratosthenes. So this painting is named after that, and sieve of Eratosthenes 900, because this one has the first 900 integers, and they're um, arranged in rows of 30, so it's base 30. And you can see like different patterns in the prime numbers. For example, you can see 29 along um, there's like a gold squiggle that goes along the diagonal axis. For some reason, I can't see my cursor, but um, you can see like different patterns in the prime numbers. And here's sort of a step-by-step of how I make these paintings. So I start with a blank canvas that I put a grid on. And in this painting, I'm going to use base 30, but I'm going to do it wrapping around. So it's going to be 1 through 15 in the first column, and then it's going to wrap around and go to 30. And then it's just going to keep snaking around like this. So this is all of the numbers filled out. And then you can see there are patterns that emerge. So when you arrange the numbers in this snaking around pattern, it's just a really nice way to visualize primes, because all of the multiples of 2, multiples of 3, and multiples of 5 fall along these columns. So these are all the multiples of 2, 3, or 5. And this is the set of prime numbers. And my painting process is basically first marking the even numbers. 2 is the first prime number, so I mark the even numbers. I mark the prime numbers. I mark all of the multiples of 2. So for example, 4, and so on. And then I mark the multiples of 3, 5, 7, 11, 13, 17, 19, 23, 29 and 31, 37 and 41, 43 and 47. And then I just continue filling in all of the other prime numbers and anywhere else that they appear as a prime factor, until I filled in the entire grid. Here's another video. This is something my friend who is a math teacher asked me to make, so it's aimed at kids. Hi, I'm Dr. Juliet. I'm from Rochester, Minnesota. I went to Mayo High School and my favorite subject was math. Today, I'll show you how I use math to create paintings like this one. We'll be painting the prime numbers and the prime factorization of the integers. We'll start with a blank 10 by 10 grid. It has the numbers 1 all the way through 10. And the second row is 11 through 20. And there are 100 squares total. 1's not a prime number, so we'll start by painting the first prime number 2, which is represented by this color blue and a small dot. Next we'll paint 4, which is 2 times 2. Then in the square for 6, we're going to paint a blue dot. And then in the square for 8, we paint 3 blue dots, 2 times 2 times 2. Every even number gets these blue dots. You'll notice that all of the multiples of 4 have 2 blue dots, and all of the multiples of 8 have 3 blue dots. All of the multiples of 16 have 4 blue dots, and so on. Next, we'll paint the prime number 3. Every 3 squares, I'm going to draw one of these triangles. This is 6. This is 9, which is 3 times 3. What's this number? It's 3 times 3 times 3. It's 27. Now let's paint the next prime number, 5. It's this magenta square. Every time there's a multiple of 5, we paint one of these magenta squares. What's 5 times 5? It's 25. The next prime number is 7. Every 7 squares, I'll draw the symbol for 7. What's 7 times 7? It's 49. The next prime number is 11. See how all of the multiples of 11 fall along this diagonal line? Next is 13. Two times 13, 3 times 13, 4 times 13, 5 times 13, 6 times 13, 7 times 13. What's this? It's 17. The next prime number is 19. The next prime number is 23. Then 29. 31. 37. 41. 43. 47. 'Now we can paint the rest of the prime numbers. All of the rest of the prime numbers are greater than 50, so they don't have any multiples that appear in the grid. What are the other prime numbers? Well, there's 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97. Now we're all done. Here's the finished painting. I decided to paint the edge green. I think it looks pretty cool. Okay, and then after I made that video, I sent it to my friend, and um, in her elementary school, the students actually used that video to create a project where they did a visualization of the prime factorization of the integers, and they had each student pick one symbol, and they each colored on the tiles, and then they ended up framing it and creating this piece of art for their school. So something that I've been getting interested in is how can I get involved in educational institutions and sort of bridge this gap between art and science? So this is one example of a project that I've done. I'm just going to show some more of my mathematical art and also pictures of um, me, showing off like the art in galleries and stuff like that. This one is also a visualization of the prime factorization of the integers, but I have it snaking around in this pattern, and it's actually in base 6. So the row, there are 6 symbols in a row. And you can see there are these little triangles, like little flags, and those are the multiples of 5 and 7. So here's this painting. Here's another one. This one, I just use lines, and you can sort of see the relationships between numbers. You can see how numbers that share common factors um, sort of line up, and they create these crisscross patterns on the grid. Here's this one in a gallery. This one's a little bit different. It kind of breaks the grid and shows like my thought process of like how I like to go on walks and think of how to solve problems. And the pattern in the center with the white squares is called an Ulam spiral, which is another way to visualize prime numbers. All right, and now I'm going to talk about my series of FFT paintings, which is my more recent series that I've been doing in the past year. This one is called frequency transformation, which I showed at the beginning of the presentation. This is a visualization of a 128-point FFT, and it actually, so like the top part of the painting shows an input signal, and the bottom part of the painting shows the spectrum and both magnitude and phase. And the middle part of the painting is like all of the computation that happens, when you're computing the FFT. And there's actually real data in this painting. Um, all of the little symbols are actually like a numerical representation of the data. The white band at the top is the input data. And then all of the little symbols are like when you're computing the FFT, what the intermediate steps are in your computer. This one is called Butterfly Network, and it's just the algorithmic structure of the FFT. This is a 32-point FFT. And again, it's the same concept where the top part kind of represents like an input signal, and the bottom part represents a spectrum in the frequency domain, and the middle part is the algorithm of the fast Fourier transform, and that's what I'll be talking about next. So again, the top part is the original domain of the signal, so it could be like a waveform for an audio signal. And it's this is just sort of an artistic representation from my mind of the signal being composed of these oscillating sinusoids of different frequencies. And the bottom section of the painting represents the frequency spectrum, and it's shown as a rainbow. The middle section of the painting, well, there's sort of two parts to it. The first part represents the bit reverse index step, which I'll talk about more in a few minutes. And the second part is called the butterfly network. And the name butterfly network actually comes from the description of the mathematical structure of the FFT in scientific literature. So one of these X shapes is traditionally called a butterfly. And you can find papers that say like efficient computation of butterfly networks. And the arrangement of the butterflies to form the data flow network of the FFT is called a butterfly network. So this is a screenshot from a book about FFTs that has some butterflies in it. All right. I'm hoping I can, let me just get out of this for a second so I can move some windows around. All right, so you're probably all familiar with the equation for the FFT and the discrete Fourier transform, but I'll just go over it as a reminder. So the discrete Fourier transform is an order n squared algorithm. So you can see the equation here. You've got k is your frequency domain index, and you're computing the large x sub k. So for each one, you're going to do this sum. The small x sub n's are your input signal elements. So in this case, n is your input domain, and you're going to multiply by this complex exponential, e to the negative 2 pi I little n k over big N. And k is a number that goes from 0 to n minus 1. And again, the computational complexity of this is n squared because at each stage, we're doing this multiplication. So we have n multiplications and n adds, or n sums. So the FFT computes this in order n log n time. So another part, well, there are a few parts of the FFT that I wanted to visualize in this painting. The first part is the roots of unity, which I visualize with these blue dots. And in this visualization, the darkness of the blue circle represents the magnitude of the angle of the root of unity. So a root of unity is a complex number that yields 1 when raised to some positive integer power n. So for example, the fourth roots of unity are 1, I, -1, and -I. And the n roots of unity are n equally spaced points on a unit circle in the complex plane. I'm just trying to get my cursor back. I'll check my cursor. Okay, great. I don't know, I'm having a little bit of technical trouble, but that's okay. So this shows the eighth roots of unity. So it's 8 equally spaced points on this unit circle in the complex plane. And so the other part of the FFT that I really wanted to visualize in this painting is the the FFT structure or the butterfly network structure. So the FFT is a recursive divide and conquer algorithm. Um, and technically it's called a radix 2 decimation and time Cooley-Tukey FFT. There's like a lot of different types of FFT algorithms out there, but this is probably the most common one or the most like traditionally well-known one that you'd see in a textbook. Um, so if you take the equation for the discrete Fourier transform and you split it up into even and odd parts, meaning the even indices and the odd indices, you get the equation at the bottom. So all we're doing is instead of just having one sum, we're doing x sub 2m and then x sub 2m plus 1. So that'll give you all of the even indices like 0, 2, 4, 6, and so on, and then all of the odd indices like 1, 3, 5, 7, and so on. And then from the second sum, you can factor out this complex exponential e to the negative 2 pi I k over m. And what you get is this recursive equation. So the FFT is it's the DFT of the even index part plus this complex exponential times the DFT of the odd index part. So at each butterfly of the FFT, the input signal is split into two parts, the even part and the odd part, and the FFT is recursively called on each part independently. And the FFT of the odd part is multiplied by the n roots of unity and then added to or subtracted from the FFT of the even part. And at each stage, you're going to be multiplying by these roots of unity. And what happens is as you go deeper in the recursion, at each stage, you're squaring the roots of unity. So say we started with an 8-point FFT. When you put in that factor of 2, instead of just using the index n, you use 2m. It's like squaring the roots of unity because you add a factor of 2 into that complex exponential. So if we had the eighth roots of unity, when you square them, you actually get the fourth roots of unity. So you can think of like doubling the angle when you square that complex exponential, you are like doubling the angle of each one. And so you end up having the fourth roots of unity, but you're going around the circle twice. And I'll show that in just a minute. So you get this butterfly network structure, and you'll traditionally see the FFT represented with this structure like this, where you have like the recursion, the n over 2 point DFT on each side for the even, the odd halves. And you'll usually just see it like as black and white lines. Like you don't really ever see it colored in with rainbows like in my painting. Here's another example. This is from the textbook, Fast Fourier Transform Algorithms and Applications. So this is called the FFT flow graph or the FFT data flow diagram or the butterfly network. And again, here's the painting. So you can see where the structure of the painting comes from. And this is an n log n algorithm. So the painting is divided up into 32 columns, and it has 5 rows, so 5 levels of recursion, because log base 2 of 32 is 5. So just again to highlight where the structure comes from, so I'm just going to highlight one butterfly on this diagram. And then this is the same butterfly. This is an 8-point FFT, but this is a 32-point FFT, but this is like the top level of recursion. So you can see where the structure comes from. And what I have in the circles are those complex exponentials, which are the roots of unity, or sometimes they're called the twiddle factors. And in the diagram, they usually use like W superscript 4, subscript n, some sort of notation like that, and I just represent them as these roots of unity, which are circles. And you can see at the lowest level of recursion, the top level of recursion, I have the 32 roots of unity, and then it gets split up. At each stage, you're dividing into the even and the odd halves, and you have the 16th roots of unity at the next level of recursion, and then the 8th roots of unity, 4th roots of unity, and then the square roots of 1, which are just 1 and -1. Um, so what you're doing here, I'm just going to explain like how the data elements sort of get reshuffled. If you label all of your data points, um, 0 through 31, these are just the indices of your data points. At each stage, you're going to split the indices by even and odd. So I've highlighted even and odd in different colors. Oops. And then we're going to send all of the even indices like 0, 2, 4, 6, 8, 10 over to the left side and recursively call the FFT on that. And then all the odd indices like 1, 3, 5, 7, 9 over to the right side and recursively call the FFT on that. And then at the next stage of recursion, again, we're going to uh, figure out which are the even indices and which are the odd indices. So on the left half, the even indices are 0, 4, 8, 12, 16, 20, 24, and 28. And those all get sent over to the leftmost half. And so you do that at each stage. So again, now we're going to split these up again and send them deeper into the recursion. And then finally, we're at the base level of recursion. So you can see we've reshuffled our data elements. So now there's this order 0, 16, 8, 24, 4, 20, and so on. And what that is it's actually if you reverse the bits of the indices. So if you represent the indices in binary and reverse them, you get this order. So you can see in the chart here, so like in decimal, the index 0, in binary, it's 0, 0, 0, 0, 0. So I'm using 5 bits because this is a 32-point FFT. And when you reverse it, it's also 0, 0, 0, 0, 0. So the reverse reverse binary index is 0. And so it's the same. It's a palindrome, and you can see I've highlighted all of the ones that stay in place in blue. And in the painting, there are these like vertical strips of blue. So 4 is another one. 4 in binary is 0, 0, 1, 0, 0. And when you reverse it, it is the same. So it's also 4 in reverse binary index. So you can see 4 is also one of these binary palindromes that stays in the same spot. But like, let's take something like 1 and 16. So 1 in binary is 0, 0, 0, 0, 1. And when you reverse it, you get 1, 0, 0, 0, 0, which is 16. So I'm going to draw a line between 1 and 16. And I also draw a line between 16 and 1. And that's where this section of the painting comes from. This I just sort of colored in these different sections. And you can see, actually, I have all of the binary written in the painting. So like there are these little tiles that kind of look like mosaic tiles. And that's actually binary on top and the reverse binary on the bottom. So when you do the FFT, it's actually, you don't really need to explicitly do the recursion. You can start just by reversing the binary and reshuffling all of your data elements. And then you can just do it in place, traveling through this flow graph. And at each stage, again, you are taking, the element from the previous level of recursion, you're taking the even part, and you're taking the odd part, you're multiplying the odd part by that root of unity, and then either adding or subtracting. And that's how you get the next element. And then you just go all the way down until you end up in the frequency domain. And you can see in the painting, there are like these little lines. It might be a little bit hard to see, but I'll show you in some other pictures, where you can see like if there's an element that goes here, there's a line that connects the starting and end points. This is just a close up of the binary indices. Another piece that I made in the series is this obelisk, and the obelisk is actually called Roots of Unity, which talks about the powers of two roots of unity that appear in the FFT. So I have the square roots of one, which are 1 and -1. You can see it's like the highest frequency, just oscillating between 1 and -1. And then in the obelisk, if you look around each side, uh, I have the fourth roots of unity, eighth roots of unity, and 16th roots of unity. And at the base of the obelisk, I actually represent the roots of unity as these complex numbers. So this is a chart of like the complex number representation and how I chose to represent it artistically. So this is the square roots of one, or the second roots of unity, and there are 8 cycles of it. So if you look in the grid, it just goes 1, -1, and then you're going to go around twice. So it's 1 again, and then -1 again, and then it just keeps going around, oscillating more times. Um, this is the fourth roots of unity, and there's 4 cycles of it. So you're going 1 I, -1, -I, and you're going around up to 4 times. This is the eighth roots of unity, and there's 2 cycles of it. And what I did in this part is I actually have these little glyphs, similar to the way I do my prime numbers paintings. There are like these little arrows and symbols in this painting that represent different numbers. So like the arrow represents square root of 2, for instance. And here's the 16th roots of unity. So uh, again, I have like the little glyphs as well as the complex number representation. And my process for painting these is actually, I usually start by writing some code in Python, and I just sort of debug the code, and I have it print out like what are all of the intermediate numbers, for my painting that had the data in it. I needed to actually compute what are the intermediate values at each stage of the FFT, and then paint numerical symbols that represent those numbers. Um, and in that painting, I actually have like a scientific notation. It was like a base 20 representation where there are like, if you look at like how floating point numbers are represented in a computer, there's like a sine and a mantissa and these different parts. And so I compute what that should be, and then I use my glyphs to represent the numbers. And then I paint all of these little symbols. So in this painting, the roots of unity, rather than representing them as circles of different value, I actually represent them as these little unit vectors that are going around the complex plane. So it's kind of like these little arrows that go around the circle at different frequencies. And this is the finished frequency transformation painting, and this was at the gallery show, Lush Computation at Seattle Central College. And this one is actually hanging up at Seattle University now. So here's a picture of me with the painting. And something that's interesting about this is people say that it looks like weaving, and it does kind of look like weaving to me, because when you take an algorithm and you sort of uh, draw it out step by step, um, it's kind of reminiscent of like using the Jacquard loom or punch cards or something, where at each stage you're you have some data and then it like goes to the next stage and it moves around, right? So it's very reminiscent of like the Jacquard loom or weaving. This one is the gallery show where I had the butterfly network painting. And finally, here's some lessons from RIT, how studying imaging science influenced my art. So one thing that I thought was very influential for me was from Carl Salvaggio's digital image processing class. If you want to understand an algorithm, draw it by hand, um, which I hope you can see how that influenced my art. Um, Another really important lesson I learned from doing note taking through NTID. There's this power in channeling ideas into handwritten notes. It forces you to really pay attention in class, process ideas quickly, and not overthink things. Just sort of have the information come into your mind and channel it through your hand. And there's something interesting that happens. When you do that, it really makes the information stick. Um, what you learn influences how you see, which is something that I learned from computer vision classes and human visual system classes. So try to seek out experiences that change how you see. Um, Another thing is optical, material, and archival properties of paint are extremely important, and paintings are much more than digital images on a screen. You know, it's a physical object that is made by hand, and you're using these paints, which are materials made of pigments, binders. It's important to understand how that works chemically, what the archival properties are, so that it holds up over time. And I enjoy using all sorts of optical effects in my work, and I'll show you a video of that next. Also, color science is extremely useful for learning to mix paint and learning how to photograph artwork well. I'm just going to share one video. Um, close up of the paint.
Earth went silent, London fell asleep. She dreamed of a winter where you appeared to me. Perfect timing as new battles in November. A tender creature, a fever, disarming, fluorescent. There you were, with your mirror, shining the world all over me. There I was, with my butterfly net, trying to catch your light. I collected stupid ashes so that after you'd gone I could hold on to something, but you stayed unwavering.
All right. So that's my presentation. I'd be happy to take any questions.
We got Danny in the front row. Go for it, Danny.
I'm just curious, in terms of planning out the process of starting the painting, how long does that take you compared to the actual painting? Because obviously you have to visualize how you're gonna lay it out, how the colors are gonna kind of be layered on top of each other. So I'm just wondering how long that takes.
Yeah, that's a great question. So the process of designing a painting, usually the first one I do in a series takes longer, because I'm not sure how it's going to work. And then as I do more of them in the same series, I can kind of like I have the shape of the FFT in my mind, and I don't really need to like plan it out. Like the first time I did a hand drawn FFT, it took a really long time to figure out exactly how to do it. And now I can sort of just do it from memory. And with these large paintings, I'm actually doing a series of them. They all sort of have the same structure with like the input signal at the top and the spectrum at the bottom. Uh, so actually painting one takes 2 to 3 months. I don't work on it like 8 hours a day or anything like that. I kind of have a lot of things going on in my studio at once, and I come in, work on it for 20 minutes, maybe I'll work on it for a few hours, and I actually paint a lot of the colors just totally intuitively, meaning I sort of choose them on the fly based on what's already there and what I think will look good based on what's there.
Very impressive.
Thank you. Any other questions?
Sure. So I guess, going all the way back to Signal Show to now, like visualizing FFTs or like visualizing things has probably been one of your strong suits. Like, were you like aware of that all the way back in high school or during your PhD? Or did that kind of stuff just kind of come naturally, like making things more like visually learning, I guess?
Yeah, I'm definitely like a visual learner, which is probably pretty obvious. And I think a lot of people in imaging science probably are visual learners. And that's why you're there. I actually first learned about FFTs in high school. So my dad is an imaging scientist. He's an MRI researcher, and that's how I got into imaging science. That's why I decided to major in imaging science. And I did a project on FFTs in high school as well, and so that's sort of where I became interested in that. And then there were some visualization aspects to that project, and I was always like, like in calculus class, like cutting up pieces of paper to show like, oh, this is like the area under the curve, and I'd make all these things by hand. So yeah, I've always been interested in that. I've always been very interested in like science writing. One of my favorite classes that I took at RIT was a science writing class, and I'm interested in science communication.
Perfect. One quick question we do ask just all the alumni. What was either your favorite class or the most important class that you took while you were here? I would guess. But...
I guess I'd have to say Fourier methods imaging, right?
Yeah. And also, do you sell those paintings? Like, because I mean, they're insane. I mean, they're crazy. They're so cool.
Thank you. Yes, I do sell them, and we're trying to get some for the department, so you may have them hanging up
That
in the
would be awesome. All right.
Forgot the counter question to the first question you asked.
Oh,
Which is
Most important.
most important class?
So you've got the opposite side.
do you have a least favorite class you
Oh.
took at RIT?
48 method.
Yeah.
No comment.
Anybody else? Ask a question. Oh, Mason, one more.
Yeah, sure. Like about like the painting you had where it was mixing walking in nature or a walk in the woods, that
Yeah.
one. Listen, I spent a summer in Seattle in Tequila. What was your favorite place to hike or walk?
So my husband and I actually go for a walk in Bridle Trails State Park, like a couple times per week. That's like our favorite place to walk. It's really beautiful there. There's horses and really large trees. Really nice park.
And
And
does
that's
that
yeah, the painting, the frequency transformation painting, the data for that actually came from going on a walk there and taking photos and then measuring the elevation from the photos. And so that's how I got the data, like the input signal, and then I computed the FFT of that. So
Awesome.
That's super cool. Well, if that is all the questions, one more round of applause, seriously. So thank you so much for being here. We really appreciate you taking your time to come and show us the artwork. It's amazing. And hopefully we get to hear from you again in the future.
yeah, thank you so much for having me. It's been a pleasure to see the imaging science department again, see all the students. Good luck, everybody. Good luck with classes.
Yeah.
Thank you.
One big thank you. for Signal Show.
Yeah, seriously. Thank you for Signal Show. That's absolutely, yeah.
You're the only reason any of us made it through linear.
Yeah. Oh, Signal
Right,
Show,
Roger?
crazy.
Me too.
But, all right. Well, thank you again and have a wonderful day.
Thank you. Bye.